wanted to go into is the difference and similarities between glass and crystals and ceramics. And there's a reason I grouped all these three together. Hopefully we'll understand why by the end of this. And there's some major differences and similarities, especially when we talk about the engineering applications for these materials. So
Yeah, first of all, I think it's important to point out that, we think in our classes like chemistry, we think of phases like solid, liquid, and gas. So we're talking about our solids, right? And glass is pretty interesting. We'll get to that one in a little bit because, it's kind of like a liquid as well. But in general, we're talking about solid materials. And if you think about single crystals, that's where essentially you see atoms at the atomic scale all lined up. They're like each atom is like a billiard ball. And if you think about on a pool table racking up that triangular thing that basically packs the balls in that way, that's really what a crystal is, where you basically pack the balls in each row, and then you keep doing this until you get a crystal. So it's a very uniform packing of atoms, and it happens on the order of centimeters or inches. It happens at a very large scale. So just an enormous number of atoms that are all pretty uniformly packed. So it's pretty amazing. And if we think about the types of crystals that most people are aware of course, diamond is probably one of the biggest ones that people think about. And diamond is just carbon that's arranged in a way that every carbon atom within that diamond that's on a diamond ring, every carbon atom's in its place. And it basically forms this 3D pattern of stacking to generate that crystal. So crystals are pretty special because they're almost perfect, right? In terms of there's no other sort of defect. They're just atoms that are perfectly aligned in every direction. So, we think about diamond, people think about quartz is another one, is a big one. That's actually not just like a single element like carbon, but it's also like silicon and oxygen. So you can have not only just one atom like carbon and diamond, but you can have like two types of atoms like silicon and oxygen that are also ordered, but they're ordered in a different way, and they're ordered in a crystal that makes quartz, like quartz crystals. So people, when they go out in the desert, they'll see these beautiful quartz crystals. But basically these are very, very large material sections that have just perfectly ordered atoms in every direction. So whether it's carbon or silicon, oxygen for quartz, it's all the same. And you can do the same with metals. Metals, there's crystals of metals as well. One way to think about it is if you ever drive along the road and you're going along and you see these patterns, on the guardrails, you'll see these like really big patches. Those are sort of like crystals that are formed. And then the other thing that's really interesting, if you look at a solar panel, they're like a blue pattern, but they have like these sections in there, almost like a mosaic, that are pretty big, maybe on the order of a few inches or centimeters. And those are crystals as well. Those are single crystal silicon. So we can see crystals in many different forms. Sometimes those crystals are not like a single unit like you're on diamond ring. Sometimes they're crystals that are kind of bonded together in certain applications as well. So metals, carbon is another one, silicon and oxygen go together. So you can make crystals out of a lot of things. Crystals are like salt crystals. People are very familiar with that. And crystals in terms of like sugar crystals. You can make it out of something that's more organic. So crystals are found everywhere, definitely.
And water, right? Ice is a crystal.
That's right.
And so that one might be good for getting an intuition for people about how crystals form and just basically how you construct a crystal, right? We can talk about seeding a crystal. They need to start with that initial pattern that basically the molecules can kind of arrange themselves around then, right? When you have a freezing body of water, that you need something for it to start. And that's why the freezing always starts around the edges of ponds and things like that.
Whenever you go through a phase change, like we talked about solids, liquids, and gases, whenever you're trying to go from one phase to another, a lot of times it's a surface that starts that change. So, one example, thinking about going from a liquid to a gas, we see bubbles start at the surface of a pot when you're boiling. And so you're basically starting to go from the liquid phase to the gas phase. The same thing happens with going from a liquid phase to a solid phase, like growing a crystal, is you need some sort of surface that basically nucleates that beginning of forming that solid phase from the liquid. You basically cool the liquid down to a point where it wants to become a crystal, but it just can't get there yet until you have some surface that allows the atoms to move to something in order. So the liquid's not very ordered. And so you need some way of ordering this material. And one of the easier ways to do is find a surface that it can basically order on. And then that allows things to get started. So that's nucleation. And then once you get things started, then of course, then it's pretty easy and the atoms sort of find their spots as the crystal grows. So yeah, that's one really nice way to grow crystals. Diamonds have to be grown at super high temperature, at super high pressures. So growing crystals is almost a skill in itself. There's lots of different methods to grow crystals. We know with growing like sugar crystals on a string, you basically you don't need a temperature gradient for that. So there's lots of different ways of growing crystals for sure.
And then it doesn't matter what kind of bond we're talking about, right? Because you talked about crystal metals, you talked about crystal hydrocarbons, and then we talked about just other molecules like carbon and silicon, and those all have different kinds of bonds between them.
That's right. So like metallic bonds, metals, we talked about quartz, which is silicon and oxygen, and that's ionic. And then the covalent bonds for silicon or for diamond are crystals that are formed with covalent. So yeah, you're right. It really doesn't matter what kind of attachment bonding is needed. As long as you can order those atoms, it kind of doesn't matter in terms of the bonding part.
Okay, let's go to the opposite, I think, of this sort of ordered structuring that we talked about in crystals, and that's with a glass.
So glasses, they're really, really interesting materials because they have some order, so they're not, a lot of them are perfectly disordered, but they're basically almost like a liquid. In fact, that they don't have this long range order. So classically, you take sand, which is silicon and oxygen, silicon dioxide, and then that's a crystalline form. A lot of times it's quartz, and then you heat it up to really high temperature, maybe like 2000 centigrade, and then you let things melt, and then you cool. And when you're cooling, if you cool fast enough, then basically the atoms don't have enough chance to arrange themselves into this crystal structure, so they kind of get locked in. And some glasses are easy to form, so you don't have to cool very quickly. And silicon and oxygen are silicon dioxide is a material that tends to form a glass. It tends to not move so quickly to form a crystalline phase. So glass is typically like your window glass and glasses on your cell phone and computer screens and all that. They tend to be silicon oxide because it just tends to be a material that doesn't need to form a crystal very easily. Some glasses, like metals, there's metal glasses, and they normally have to cool those really fast. So they melt the metal. And normally what they'll do too is they'll put a lot of different atoms together. It won't be just one metal to kind of mix things up, so it's not easy to order. And then you cool very quickly. A lot of times they'll do a splat. We'll have this wheel that's really cool, and then they'll basically drop the molten liquid, and they'll form like these ribbons of metal glass. They call it met glass. So you can really make materials that don't want to be a glass. You can make them a glass if you cool them fast enough. So the cooling rate from the liquid is really important.
And then, so you talked about cooling metals really fast to form glass. What is the most metal that we think of that you melt and form into a shape?
Yeah, so those are going to be polycrystalline. They're almost, so, we're going to talk about ceramics as well. So those have many smaller crystals. So going back to the silicon crystals that are in your solar panel, they're really pretty big. Just imagine now those centimeter sort of crystals that are bonded together are now on, say, the micron or nanoscale. So it's really, ceramics are just crystals assembled that are on a small scale, and they're somewhat randomly oriented. They're kind of glued together haphazardly. And so then that's really a definition of a ceramic, which would be like an oxide like quartz, but metals have polycrystalline as well. So you have polycrystalline oxides, they're ceramics, and then you have polycrystalline metals, but they're both pretty similar in terms of having this type of structure. And the reason why oxides are so big is because we live in an oxygen environment, and not many metals survive our atmosphere. And so everything you dig up out of the earth is going to be a ceramic. So, and the ceramic tends to be an oxide. So that's why ceramics are such a big word, even though, there's they're polycrystalline and there's polycrystalline metals, but you don't call those, they don't have a special name. They're just still metals. Whereas, you go from a single crystal quartz to a polycrystalline quartz, and now you call it ceramic. I mean, there's no analogy for metals, but it's 3 millennia of people working with ceramics that's why it gets called ceramics.
Yeah, so talk a little bit about the manufacturing process of ceramics then. I guess if we don't call rock ceramics typically, it's normally referred to as some sort of manufacturing process that makes them a ceramic, right?
Absolutely, yeah. That's right. So traditionally, I mean, ceramics, everyone knows, have been around for a very long time. So there's some real basic ways to make ceramics. You think about clay pots and that sort of thing. You just mix some water with like a powdery substance, and the water acts as a natural glue for clays. For some of the more technical ceramics, you have to add your own glue. So not every ceramic is as nice as clay in terms of forming. So clay is pretty amazing. When you start adding water, you form this mix that has its own sort of plasticity. In itself, clay is a pretty amazing material. The technical ceramics are made a little differently. Like if you think about electronic components, there's a lot of electronic components made of ceramics. There's substrates that you use to populate like high temperature chips and stuff like that. And these tend to be like aluminum oxide. And there, they tend to use something called tape casting. And tape casting is where you take a slurry, and a slurry is just a mixture of a liquid with the powder in there. And then you pour the slurry on glass, and then you smear it out with something called a doctor blade. And the doctor blade's set at a height, maybe sometimes it's tens of microns, so pretty thin. And that slurry then dries, the solvent comes off, leaving the ceramic particles on the plate. But then there's also a little bit of glue, like a plastic that keeps all the particles together. And so you then can peel it off, and then you can start laminating. You could start printing on that, almost like paper. It's a lot like paper. And so that's the way circuits are made. So when you go from, say, you want to take the signals out of a chip and go to another chip, you could either use that green board you see on your computers, with the traces, or you could use these really little ceramic chips to bond the silicon chips on. And those are very fast and very efficient. So that's another ceramic process called tape casting. So yeah, a lot of ceramic processing is very traditional, but then there's new ones that are pretty interesting for making technological components, which is pretty important. For example, multi-layer ceramic capacitors. There were well over 1 trillion made last year. So it's a huge business. There's hundreds of these multi-layer ceramic capacitors in your cell phone, hundreds in your computer. So it's sort of a big business, and companies have really gotten good at ceramic processing to make these sorts of chip capacitors out of ceramic.
They basically come from clay or some small particles that you just stick together, right? When I was learning this, I thought of it as like packing a snowball, basically, right? You have a bunch of little snowflakes, you stick them together, and as you press harder and harder, and it warms up a little bit, particles start to stick together then, right?
But then you have to heat it. So that's only the first part. And I guess that's one thing I didn't talk about. So that brings up something called sintering. So that's what the kiln is for. So now do you form this great nice shape. You've made your pot, and you want to fire it, right? So what does that do? So you mentioned the snowball where you're basically packing. Well, when you pack something, it may be like 50% solid, but there's a lot of air, maybe 50% air. And so how do you get rid of that? You can only press on things so much to get that air out, and you still have maybe 20, 30% by volume air, maybe more. How do you get rid of that? Well, you heat it up to really high temperatures, glowing red hot, And then once you do that, then actually the atoms of each particle start moving to minimize the surface. And then they basically kind of glue the particles together. There's people who study sintering for a living, but basically it's just minimizing the amount of porosity within the ceramic. So you go to high temperature, some ceramics sinter at 1500 centigrade, so 3000 Fahrenheit and above. So you have to go really hot. Some of the really technical ceramics, you have to go very high in temperature. So that's another definition of a ceramic, something you have to process like that.
There's a reason that so many ceramics and glasses and things are made of silicon oxide, right? Partly because of its prevalence. I looked up, I guess 90% of the minerals in the Earth's surface are silicate. So if you go out and find a random rock, it's probably some kind of silicon oxide. So is that what we do? And people talk about making glasses, just melted sand, right?
There's lots of glasses, but it turns out we're really lucky to have silicon oxide as in terms of glass forming. There's only a few elements that form glasses. So there's boron oxide, there's silicon oxide, and then phosphorus oxide is a big one. And those are the main ones, I think, for forming glasses. But silicon oxide is sort of by far the best one. It really structurally is the best as well. Like boron oxide just dissolves in water, so you wouldn't want that. You wouldn't want pure boron oxide. But they do put boron oxide with silicon oxide, like Pyrex. It's sort of a classic mixture of boron oxide and silicon oxide. So the boron is used to minimize the thermal shock, and silicon oxide is robust. So mixing boron oxide, silicon oxide is sort of a big deal, and it was discovered quite a long time ago in terms of a very special glass with good thermal shock capabilities, so good mechanical properties. Yeah, I mean, we're really lucky to live on Earth with silicon oxide, I guess, in terms of for the glass industry. I don't know. There's not a better material for making glass. We're kind of lucky.
Okay, good. And let's just jump right into some of the more applications and engineering of glass then. Of course, we can see through it. So maybe let's start with the optical properties and why you can see through glass.
Yeah, so glass, of course, is probably one of the best optical properties materials out there. Basically, if you look at sort of transparent materials, that first of all, glass doesn't have any sort of boundaries. We talk about ceramics, we talk about gluing crystals together. As soon as you have a boundary, light's going to scatter off that boundary, could scatter back to you, or could just scatter just at a certain angle. And so it's going to be opaque. And so glass is perfect because the atoms are random, but there's no distinct boundaries within the glass. It's just inside the glass, you look one way, it's like, well, there's a bunch of random atoms, but I don't see any interfaces. And I look down the other side, and, like a ceramic, you would see an interface. Here, it all looks the same. So there's no scattering of light. That's one of the big reasons why glass works so well. The only boundaries are the front face and the back face of the glass. That's it. Whereas in polycrystal materials, there's thousands of boundaries it scatters off of. Once you get rid of the boundaries, like glass has no boundaries, now the light can go through. And then the next thing you think about is at the atom scale. And can these atoms absorb light? And some atoms absorb light better than other atoms. Silicon oxide, silicon nor oxygen, really absorbs the light in the visible range. So then it basically just lets everything through. And so it has an incredible transparency. There's very little loss of light as the light passes through glass. And of course, probably the best example of that is an optical fiber, where light can go, kilometers and still travel. And of course, that was a great development where the glass was ultra pure. They made it ultra pure and draw it down into a fiber. So yeah, that's sort of the ultimate when it comes to light transmission is fiber optics, which is something pretty amazing. Yeah.
So they're not tubes that are shooting light through. It's just a solid fiber of glass.
Yeah, essentially it's very pure glass, and silicon oxide is a big part of it. There's some other elements as well, but silicon oxide is the big one.
Mm-hmm. And then I want to stick with glass, but is that why silicon oxide crystals are transparent as well? because for the
It
same
ha-
reason that glasses, or is there something
yeah,
different?
without getting into it too much, there's something called a band gap in all these materials. The band gap is the ability for an electron to jump from one band to another band. And when a light comes in, if the light has enough energy to make that electron jump, it'll absorb, right? And so silicon has a much smaller band gap, like almost 10 times lower band gap than silicon oxide. Silicon oxide has a huge band gap. So no matter what hits it, the energy of that light is not sufficient to make the electrons jump, so it won't absorb. It'll just basically allow to transmit. But silicon, it's small enough that you can get those light to go in and make those electrons jump and they absorb, right? So that's one of the big differences between silicon and silicon oxide in
Mhm.
terms of not trans silicon by itself looks almost like a metal.
And so that's more or less what people learn in their first chemistry class, where you talk about mostly gases.
And re-emitting, absorbing, re-emitting, that sort of
Okay,
thing. But
so it's the
certainly
same thing
absorbing.
for solids, and it's just that
Yeah,
most solids have a whole bunch of ways to absorb or
we have
reflect
some
light.
different ways to do it, not separate atoms, but as groups of atoms, they absorb differently. And so
Okay.
that in class is pretty interesting because silicon oxide has this huge gap. And basically, then when the light goes through, it doesn't sort of make these electrons jump. So that's the first thing. But you can add things to glass, like iron, for example, is a good one where iron will absorb certain wavelengths of light. And then that green glass you see, that's something that's pretty common. So the light, basically the red light, I guess, is getting absorbed and only allowed the green to pass through. And so then yeah, so that's very special maybe to iron. I think cobalt is a very beautiful blue. So, that absorbs at a different wavelength to allow blue to pass through. So those are additives that each of these elements that are spread out within the glass will absorb.
Yeah, and you don't see it too much anymore, of course, because polymers can select for that very well. So,
Yeah, that's right. Polymers that can do a lot these days for sure.
okay, but there it definitely is still some uses for glass. We don't have polymer windshields or windows in our house, things like that. Those are still made of glass.
We kind of have polymer windshields
Oh, is that
because
right?
it's layered, right? So like
Okay.
windshields have I don't know how many layers, but they'll have some polymer in between the glass to basically toughen it up. And so if the glass breaks, there's a polymer layer that kind of keeps it all together. So windshields are definitely made of a layered composite, I believe, with polymer glass and maybe polymer glass. I just don't know the structure too much, but certainly polymers are used quite a bit in some of these structural applications
Okay.
for sure. Yeah.
Okay.
Yeah.
But you still have glass in it, right? And why
Oh,
do we
absolutely.
have
Yeah.
glass instead of just a pure polymer for things like that? So what does glass do in terms of, we talked about the optical part of it, but the mechanical part, because we make these big windows, big tough windshields, aquariums, those are still,
Yeah.
big thick glass. Yeah, yeah, right. Phones
That's the
even.
big one.
Why do we have glass screens instead of polymer screens on our phone?
Yeah, so glass screens are pretty interesting. Like on cell phones, the Gorilla Glass is one that's pretty common. And so what they'll do for the glass that's on your cell phone is, obviously, you can drop it. Sometimes it will break, but a lot of times it won't. And the reason why is because they've made these glasses really strong. Basically, what will happen is you'll have a thin piece of glass, and we talked about glass being mostly silicon oxide, but there are other things they add into it, like sodium they'll add in, and that helps lower the melting point, make it easy to process. And then what they'll do is they'll take a solution of potassium, and potassium is a bigger ion. And then what they'll do is they'll exchange the potassium for the sodium. So they'll bring potassium in, sodium leaves. And so what's really interesting about that is now you take a big ion, put it into where the small guy was, and he creates this really compressive, because it's squeezing it in there. And so it makes the top layer of the glass in compression. And so then it resists any scratching, any cracking at that first part. So it's an ion exchange glass, and it's really what makes Gorilla Glass so special and so tough to break, because it's already got compression. And most glass and all ceramics normally break in tension. And so if you can keep the surface in compression, it goes a long way to making the ceramic more mechanically stable. I guess the other one to think about, ceramics and glass people have always thought about, how to manage stress within the material. Another good example is Corel. So for example, in Corel, you have multi-layers, and the outside layer also is a glass, and it basically cools at a different rate. It has, and I don't know all the details, but basically it'll cool. So the outside's in compression and the inside's in tension. And so, because obviously you have to balance the stresses, it's not like the plate's moving around or anything. And so you have to balance the stresses. So the outside is in compression, inside in tension, and that really makes for a strong plate. They don't scratch, they don't break easily. But once you break something that's a Corel dish, it explodes. Why? Because as soon as that crack makes it to the center's in tension, it just pulls itself apart. So, these dishes are pretty amazing until they're not. And then they'll just kind of blow up all over the place because of this huge tension in the middle. And so, yeah, people control in glass the stress states of the glass. Tempered glass is another one, right? So that's a way to form glass that has compression on the outside. And so that's what they call tempered glass.
Okay,
for,
tempered steel you hear about as
Yeah.
well is probably the
Yeah.
same process, but with metal. Okay. And then why does it, like, if you'll see videos of people who like chip the corner of a big pane of glass or something, or maybe you slam the door or something, and it just like spiders all the way through the whole thing. Is that the same principle?
Yep.
That's
Yep.
okay.
So basically the inside's sitting there just poised to break apart, and you hope you never get to that point where the crack makes it to the center where it's in tension. And they actually designed these things also to break into small pieces. So they designed the stress states so you don't have these big jagged pieces. It just kind of almost is like a bunch of little pieces, and it's less dangerous as well. So there's a lot of technology that goes into designing stress states of glass to do things like that.
A really dramatic example I've seen online. There's some cool YouTube videos of where they drop molten glass into a bucket of water, and it forms these drops that are like super hard. You bang on them with a hammer, they shoot them with bullets and stuff. They're really cool. I definitely recommend people check out these
What do they
videos.
call those? The
Prince Rupert drop.
Prince Rupert drops, right? Yeah.
Yeah.
And you kind of just touch the tail a little bit, and the thing just goes.
Yeah, it just explodes
Right.
then. Just one little crack. Yeah, so that's pretty cool.
Yeah, that's a great example of how you have the outside of that Prince Rupert drop in compression, and as soon as you break through that compressive layer, you get to the point where it just explodes.
Yeah, let's stick with glass a little bit. Fiber. So fiberglass, and you talked about fiber optics. These are both glass, but they're like flexible.
Yeah, right. So think about mechanical properties. So if you think about stress on some body, the thinner it is, you can bend it more and have less stress at the surface. So it really is a mechanics problem. So it's independent of the type of material. It's just the way the stress state of the material is. If it's really thin, then you're not having much stress at the surface. Even though you're bending it down, there's not much tension at the surface. And the thinner you go for a given bend radius, you'll have less and less stress at the surface. So for a fiber, you can actually wrap it around your finger, mainly because it's so thin that there's very little stress at that outside surface. Whereas if you try to take something that was really thick and try to wrap that around, it's going to be so much stress it'll just break. So it really is more of a mechanics thing than, I guess, a material thing. I will say one thing though, fibers are made in a way that there's no defects, right? So all around that circumference, if you draw a fiber down, it's pristine glass, and there's very little defects on that surface. Whereas if you bend the plate, the first place it's going to break is at the edges. So if you cut the glass, you're going to put little defects in those edges, all along the edges. And any of those little defects, as soon as you put a little bit of stress on, they'll propagate and crack. So fibers are pretty special because you're bending, and there's no cut defects in any of them and around that circumference. So it really has to do not only with sort of the stress state, but also there's just no initiating flaws or defects like in a flat plate where, you have a finite flat plate, there's going to be some edge. That edge is going to have a defect, and that's where you're going to get your crack started. The other thing they kind of do, though, I think they coat the fibers with a little bit of polymer just to kind of keep the defects down as well. Because you put a little nick in there and it'll just go. Yeah, that's one thing about glass. If you just start with a little bit of a nick or a crack, it'll just propagate.
Yeah, fiber optics are probably even thicker, I would think, than like fiberglass insulation, or those just feel like cloth, like they're so thin and flexible. And
Because like a lot of these fibers are made, very quickly, and they're put into like a glass wool or something like that. Or sometimes they'll add it to the green board that they use in the computers, and that the fiberglass will be added there. Of course, fiberglass is used as a structural material when you mix it with epoxy,
right,
the fiber.
right.
Yeah.
Okay, let's do one more. Let's do glass cooktops. Talk to me about those, because I know you like them.
Yeah, glass ceramics. So now
Oh,
we've talked
it's a
about,
ceramic. You want to do ceramics first, and we can combine
no,
them.
it is a glass ceramic.
Okay.
So I'm doing glass and ceramics.
Okay.
So what's really neat about cooktops is they start out as a glass. And so, you pour and you start it out. But then what they'll do is a special heat treatment process that they'll grow these really tiny, tiny crystals. And basically all the glass will be transformed into a crystal. And that's a very special material because it's really tough and it's very mechanically durable. And so that's why cooktops are just made with these. And so they look like glass, but they're called glass ceramics. It was actually developed by a scientist who kind of made a little bit of a mistake one night and left the glass in too long during heat treatment, and basically formed this glass ceramic. And he pulled out a furnace and he dropped it and it didn't break. And then after further investigation, they realized that the glass basically turned into a crystalline material, but the crystals were so small that it really made the material mechanically really strong. So I think we talked about how little scratches will cause glass to break. What's really neat about glass ceramic is if you have a little scratch, that scratch will stop because it'll get blunted, because that crack will kind of move along that boundary and basically lose its energy. So glass ceramics are really interesting because they're super tough. They'll take a lot of mechanical beating, a lot of thermal shocking, that sort of thing. So yeah, so cooktops are actually ceramics, but they started life out as a glass. So yeah, that's a pretty nice story. And that's actually a fairly recent development. You think about glass being around 3,000 years or something. Glass ceramics have been around maybe 100.
That's a good transition. We talked about some applications of ceramics. You talked about all the different manufacturing processes and how they're pretty specialized for the application. You'll see the ball bearings now are often being substituted. You even see ceramic knives and things like that. Yeah. So do you want to talk about why that is? Like, I suppose they're hard, but
that's why
they're often, yeah. But I suppose the normal problem is just that they're brittle, right? That seems to be always the trade-off with all these sort of materials, is the brittleness versus the hardness. If you want to just maybe talk a little bit more about how that works and how we engineer those different materials.
Yeah. So when we talk about ceramics failing, they always tend to fail in tension. So what that means, if you have a crack that's starting to open, at the very tip of the crack, ceramics don't blunt most of the stresses at the crack tip. And so what happens is in metals, the metal around that crack tip will flow a little bit and deform to basically blunt the stress at that crack tip. So if you can figure out ways and applications where mostly the application for the ceramic, if it's in compression, you don't really worry about opening up that crack. It's basically you're always compressing, right? So that when you think about a ball bearing, you think about mostly compression, right? Running in a raceway and supporting something. And you mostly think about that application, that ball bearing being in compression. And so that's sort of an ideal scenario for ceramics, is they don't really fail as much in compression as they do in tension. The other thing that's really nice about ball bearings especially is the wear, right? So ceramics just don't wear out. They don't wear out like metals. And we think about ceramic knives, you can hold the edge, right? So you can hold the edge much better in a ceramic knife than a metal, where it sort of blunts and, sort of basically over time will wear down. So in any wear application involving compression, ceramics are really, really good at that.
Mhm. So yeah, when we think of hardness, normally think of like their ability to scratch each other or something, but there's also uh metal ball bearings get kind of squished, you can see sometimes, right? Are those different properties that relate to being squished versus being like scratched, or are they the same thing?
Well, scratching, but basically the plasticity part of squishing versus the plasticity part of blunting that crack, that is the same thing. So for metals, that's why metals work so well, because they're able to plastically deform under stress. So you could even think about plastic deforming, about squishing the ball bearing, or just like blunting a crack. That both is the same reason for metals anyway. I wanted to go back to hardness though. So of course the hardest material is diamond, and so that sets the bar for the scale. And then the next ones are ceramics. So like zirconium oxide, you can actually fake diamonds or zirconium oxide, but you can also make a ceramic out of it. And that is a classic ceramic that is really a lot of hardness to it. And of course, silicon nitride and silicon carbide, these are really hard ceramic materials. So that's one reason why ceramics are used in all these, like, cutting bits and stuff like that, tool bits, stuff like that.
So the hardness also probably matters a lot. I know they make bulletproof vests now out of ceramic plates and not metal plates. So the hardness there, I guess, matters more in some sense than the brittleness when you're
Right,
comparing
that's right.
metals.
Because the metal, because it deforms, it may not stop a projectile, right? I mean, you think about a projectile coming in and then the metal plastically deforms. Well, it can't plastically form too much, because then it'll allow the projectile to pass through. I'm not an expert in this area, but I can see that being one of the reasons why metals. Also, it's just the density of these. Like, metals are like 5 times more dense than ceramics. So just the weight factor probably also affects, like I said, I'm not an expert, there's a lot of armor experts, but these are like silicon carbide, it's probably silicon nitride, I'm guessing, where they make these plates and they just, put it in a vest, and they're not shaped. I don't think they're shape form. I know they're trying to, but a lot of them are just pockets you put them in, and once they are used and saved your life, I guess they just kind of put a new one in, and that's it. So yeah, I think the hardness helps a lot and prevents a lot of penetration that way. And the strength to weight ratio is really high.
Mm.
So I think those are all really important for designing armor for sure. Ceramics are pretty light in comparison to metals.
Okay. A few more applications I want to go through just that I think are cool for ceramics. Space shuttle tiles, of course, are
Yeah,
famously.
I was gonna mention that one. That's how I got into materials in the first place. So the space shuttle has on the outside of it a thermal heat shield made of, I think it's mostly silica, where it's a very, very porous material that doesn't allow much heat to be transferred. It's pretty amazing. So they put these shuttle tiles, on the outside, and once it goes through the atmosphere, it heats up, but basically keeps everything pretty cool on the other side. But the temperatures that they get to, you need something like a ceramic, because not only does it have to have good thermal properties, low thermal conductivity, but it also has to be able to handle that heat. So it tends to be really porous, really small, fine particles that are glued together, but with a lot of air in between. And mechanical properties are tough, because you can imagine something like a sponge made of these particles, and the mechanical properties are really hard to, so it's hard to optimize the mechanical properties and the thermal properties. So the engineers who designed these thermal spatial tiles had to really consider both of them and sort of maximize both. And of course, we know that there still was some problems on them adhering and staying on, and that's the mechanical part, right? So you're trying to average the or optimize, I should say, the mechanical and thermal, but certainly a really cool application.
And relatively light, I would assume, like you said, because
Yep.
that's really important for
Aerospace,
yeah.
absolutely. Yeah.
Okay. Okay, good. And spark plugs are also.
So the really good insulators And so, an insulator is, for example, something like your plug in the wall is polymer, mostly is plastic, and you have two wires coming out of your wall and they're surrounded by this plastic. Well, that's just fine. You could offset that voltage, normally 100 volts or so. The spark plugs tend to be at very high voltages, not much in terms of current, but a lot of voltage. And they have to run at high temperature, right? So now you got this really tough environment. It's basically at the top of the piston. And so you got a really rough environment, a lot of heat, a lot of vibration. And so ceramics are really the only material that can be an insulator, which means not conduct electricity and handle the heat. And so that's a really interesting application. And one of the biggest things they have to do is they have to make the ceramic thick enough to support the voltages, which are, I don't know, kilovolts or something like that. So, you have to worry about the dielectric breakdown. It's almost like the mechanical breakdown, but in this case, it's enough of a voltage that will fail the material. So ceramics are really good at holding high voltage. For example, if you go just look at utility poles outside, you'll see like on the really high voltage wires, you'll see these sort of things that are connecting them, and those are ceramic. And you'll see sort of these things, they almost look like upside down dishes. And those are basically isolating the different wires, and that's a ceramic as well, or glass. Sometimes they use glass. And so for any of these electrical insulation applications, ceramics and glass are really, really useful.
Mm-hmm. So I always wondered, so they're good, both electric and thermal insulators. Is there a relationship between those two? I always wondered.
Yeah, absolutely. So like metals, a lot of the thermal conduction in metals is just electrons being transferred. So it has to do with electrons carrying the energy from one side to the other. So yeah, if you have an electrical insulator, that means the electrons aren't really traveling. And so they're not carrying electricity, nor are they carrying heat. They're basically eliminated the one mechanism of transferring heat in a material. It's electronic. Yeah.
Okay.
So metals are sort of really good thermal conductors normally. So they do go. And that's one of the biggest problems, trying to find a material that's a good electrical conductor, but a poor thermal conductor. There are applications for that, and people are working like crazy to find that. And for energy applications, if someone found that, that'd be big. That'd be huge.
I guess just the final sort of obvious one, I don't know why I didn't think of it before, is just bricks. Bricks are ceramic, right?
Absolutely. Yeah.
But
yeah.
So that's a very common building material, of course, but I want to contrast that a little bit with concrete, because concrete is not a ceramic.
Well, the ceramic society takes credit for it. So basically, concrete is chemically bonded. So you still have these particles, but there's a chemical reaction that occurs in concrete that basically the concrete gets set up, and the bonding process between the particles is a chemical process. So that's cement. In bricks, it's just what we've been talking about in terms of sintering. You have to heat up to high temperature, and then the particles bond at high temperature. So one's like almost like a room temperature chemical bond, and the other one's a high temperature bond, or the particles are glued together there. I will say one thing with bricks: what really bonds the particles of clay together is a lot of times is glass. These ceramics actually can have glass as the glue as well. Even though you don't think of glass in these ceramics, there's a lot of glass that's located within ceramics as well. So it's like you think of glass as only something you see through like a window, but glass could be in a lot of things you just don't realize, that it's crystal and ceramic together. Or sorry, ceramic has crystal and amorphous or glass phase.
Do you want to go back to manufacturing some crystals and talk about those applications too?
So single crystals are a big deal for semiconductors, right? So silicon is the king of semiconductors. They've really worked on ways of growing these crystals that they're, I don't know, they're like, 16, 20 inches. I don't know how big, but just enormous diameter. These are boules, and then they stand as tall as like maybe 2 meters, something like that. I don't have all the details, but they can grow these by basically having a pool of liquid silicon. They heat it up to, I don't know, 2000 centigrade or something, maybe even higher, I don't know. And then they basically come down with a little seed, and then they'll start pulling that up. That's an amazing process. that they've developed over the years. And of course, then they'll slice it like a salami to make the crystal planes that you basically do all your transistors on. So that's been amazing. That technology is there. It's really mature. One of the bigger challenges is silicon carbide. So what's happening these days, as we push into 5G and we make power semiconductors for all kinds of applications, what's transforming all this are new materials called wide bandgap semiconductors, and that's not silicon. These are things like silicon carbide, aluminum nitride, and these are going to drive the next generation of power delivery systems and also communications. Computers probably still be silicon for a long time. And what's really interesting is those are very hard to grow in the way I just described, because silicon and carbon, if you try to grow it in a like a boule like that, the temperatures I think are too big, too high, and it's just impossible. So they grow a lot of times by a vapor phase. So they take a gas and they'll take the gas and they'll, instead of growing from a liquid, they'll grow from a gas. You can imagine how much more time that takes, because it's just an incredibly laborious process. So that's cost, right? So can we ever get the cost out of making these huge crystals of silicon carbide? That's really big. And plus now you only have, in silicon, you have one element. So your job is to organize those silicon atoms in 3 directions perfectly. All right, that's hard to do, but they do it in these big boules. Now you double the problem if you have silicon and carbon that you have to do this with. So silicon, carbon, silicon. So now all of a sudden defects become a really big deal as well when you start growing these crystals, and defects really kill the electrical properties. So that's one of the biggest challenges in the future, growing these huge crystals to commercialize the next generation of power devices and telecommunication devices by getting these crystals to be big and processes to make them. So that's really our future. And gallium nitride is another one. That's another one that they can't even grow very well. They actually put it on sapphire, which is a single crystal of aluminum oxide. So I would say that's one of the bigger technical challenges, is to figure out a low-cost way to make these crystals, just like silicon, which is amazing.
Are there any other big applications of crystals or silicon crystals in particular, besides these electronic silicon wafers, chips,
Wide bandgap semiconductors like gallium nitride, has transformed like the cell phone industry, right? In terms of pushing frequencies up. And silicon carbide has transformed the power electronics, where you're basically looking at automotive, hybrid vehicles, switching from DC to AC. You have DC batteries and you have AC motors on the wheels. How do you do that? Well, you have these switches that are made of silicon carbide, and it's much more efficient. They can run hotter than silicon, so it's really transforming the way energy is being processed from DC to AC, up converting, down converting, machines, motors, that sort of thing. So yeah, it's sort of a big deal. Silicon carbide, of course, is used in LEDs for lights as well. So companies have done that, and we know how well LEDs have done in the world. So that is another huge application of crystals.
And those don't have to be 2 meters tall. They can be pretty small.
They can be pretty small, and of course they've worked out it, and they're pretty cheap, right? They're competing with incandescent bulbs very well.
Okay. Are there any other applications you see sort of in the future, or fields to watch that you think are primed for advancement?
Materials are interesting. Like you think of like apps, developing apps for your phones, they happen overnight, or maybe an AI application or something that happens within 6 months to a year. Materials are really different because it takes a long time to develop them, and then to get them in a processable form in large scale. So all these things take time, decades sometimes, for a new material to be put into a mainstream application. So, there's always being new ideas and new processes and tweaking materials, and that's always happening in the background. But in terms of like a game changer material, I wish I could say we could develop something tomorrow and it'll just be out there. But there's just so many things that have to be done in the material world in terms of setting up the process to make it, and then making sure that that it connects well with the other materials. And so it's just seems like the materials world moves a little bit at a slower pace than, say, the software world. But certainly there's a lot of excitement I see in telecommunications as we push into 5G. People want to push into 6G, even higher frequencies. So the last frontier of the electromagnetic spectrum is called the terahertz frequency range. And so people are trying to push up because then you get even better bandwidths, you get lower latency. So people are always pushing frequency up. And of course, we're looking at pushing up frequencies for cell phones, and that's happening now. And materials are riding along with that.
That kind of answers, but I wanted to ask you, since this is the second time you've been on, and the first time we talked about microwave, which on the surface may seem kind of unrelated to ceramics and glass materials, but I guess there's a reason why I had you on to talk about both microwaves and ceramics. Do you want to tell me why you study both of these things? That last
Yes. So what's kind of exciting right now for us is like as we go from 4G to 5G, what will happen is the signals will become short. They'll be traveling shorter distances. So that's a challenge, because right now maybe cell phone base stations may be a few kilometers apart. I don't know, something like that. But with 5G, the newest 5G at higher frequencies, these base stations need to go from kilometers apart to maybe hundreds of meters apart. So you think about that in terms of area, that's just a huge number of new base stations, right? And so because the frequencies are higher and the propagation lengths are shorter, the other thing that happens is that these wavelengths are small enough that you can't bend around. So these waves won't bend around buildings. And so what you have to do now is shoot the beam and reflect off like a window to get to that cell phone. And so maybe the signal it's like playing, ping pong or billiards or something. I don't know. And so you're basically trying to find a phone maybe with 5 different reflections. And so that's the future for a lot of telecommunications. Obviously, it'll happen in cities versus rural areas first with the buildings. And so that's been really fun for us to think about those materials.
That's good. That's all I have. Thank you very much. I've taken a course on this and I needed you to explain all this to me again.
All right. We're still learning.